Hello, everyone. People in the room, people online. Welcome to our Houston Electric Vehicle Association meeting for April 2026, second Thursday as usual. Of course, we're going to have more activities, this being Drive Electric Earth Month. So, Colin, if you want to pull up the start meeting slides. We've got exciting things happening. So I know our vice president is off talking to some other folks, and he's involved in the art car parade, which is a big tradition in Houston. As I was mentioning to someone just a few minutes ago, unfortunately, a lot of those vehicles are highly polluting vehicles because people take their old cars that aren't reliable enough for the serve as daily drivers and they decorate them as art cars. But of course, most of those have tailpipes that put out quite a bit. So, but hopefully, in the coming years, more and more EVs will end up in the art car parade of Houston because that's really a big annual event in Houston. So, okay, so some of our past events in the Spring Branch Independent School District, they had Career Day, and thank you, Colin, and other folks who went out there and talked to all the young folks. That's really nice to get them excited about things that they're looking forward to in the future. So you can see some various things here in the photos. I especially like in the upper corner, what do you call your little crazy car? The crazy car, which just spins you around and then zooms off down the sidewalk at tremendous speed, and it's all electric and it's super fun. So that's always great to have out. We've had it out at the Houston Botanic Garden and at other events we've done in the past. So I'm sure the students just loved having the crazy car out there. It was fun. Okay, good. And the day for the art car parade. Oh, today the art car parade has several different days, and today is one of them. So in the lower right, you can see our vice president there, David Lowy, and lots of kids and stuff. And he's put some decorations on an EV, so there's at least one EV involved. And today was going to different schools. Okay, the art car parade has different events over a period of time here in April. So today's visiting different schools because they will have a parade. I believe it's on Saturday from Allen Parkway around City Hall and back to Allen Parkway. So people can look up through the media where they might want to stand if you want to watch the cars parade by. Okay, so 9th to the 12th, as they say. And then coming up on Saturday, the 25th, we will be in the center of Houston, right across from the George R. Brown Convention Center at Discovery Green. And we always appreciate when our members will bring their cars out and then they give us a section of sidewalk usually or a little patio area next to a building so you can see from past years. We like all different makes and models of EVs, especially if we can have a homebrew type EV. That's really nice to show folks what can be done to take older gasoline burning vehicles and turn them into modern EVs. And so you can go online to sign yourself and your vehicle up. There's just a few questions there. They like to ask how many EV miles you drive per year and things like that, just so they have a few statistics. And so that's about that. Oh, okay, you jumped over. So for folks on the south side of Houston, the lunch meeting will be down in League City at the Red River Barbecue. You can see the address there on Main Street of League City. And it's just an opportunity. Usually we have 10, 12 folks. We'd all just sit around, eat the food that everybody buys individually, and talk about car projects or as we were talking about here just a few minutes ago in the room, the donut battery and is it real? Things like that. So that's kind of for the south side. The art car parade, as I mentioned, is kind of in downtown area. And Batteries and Brews, we're going to do this month on April 26th, a Sunday, from 1 to 3 over at Watershed, which is on West Belfort. So that kind of hits the southwest side of town. Next month, we'll see whether we want to do it there or do it at another location. We like to kind of move it around. So I'm perfectly welcome to any other suggestions, a place that you think would be nice. It's got kind of a quiet area. They have some maybe craft brews or whatever. In particular, Watershed has got some German food. You can get a sausage plate and things like that if you'd like. But the idea is, again, just to get together to chat. You can kind of see we're sitting around by the windows there. Yeah, there's that. Of course, we can look out the windows and see the cars that everybody drove in that day too, which is kind of nice there. We've done it at a few different places. We've done it at Watershed more often than any others, but some people have suggested some, and so we'll see what we want to do for May, June, July, so forth. And of course, the national organization likes folks who sign up. Here, our chapter, we have no dues for the chapter, but if you'd like to stay in touch with things happening nationally, there's a small annual fee, and then we collect a little bit of that, and it helps us just print out some materials once in a while. We don't really spend very much money since we do everything with volunteers. And one thing that we get from National are these one sheets, which are nice because it is an easy way for folks to get an overview of what kind of vehicles are out on the market, for folks that may be in the market to buy a first or a second or a third EV. And we have some business cards over there so if people can get information about our website and our Facebook and other things. So this is always good to tell people. And then under opportunities, EV test drive events, we always like when we can organize those. Anyone who's got an idea of a topic they can either present or that they would like to hear about, we always like to look into different areas of technology and so forth. We might do trivia night, we'll have to see. And then there's the Generation 180, which the national organization is promoting, and that's tied to different band concerts. And so what they're offering is talk EVs for tickets. So maybe that'll encourage some people to volunteer. They get the chance to go see their favorite band that might be hard to get tickets for. I thought that was really ingenious. Yeah. Yep, a new approach. So, okay. And Facebook, you can look at Facebook. Different members like to post things. There's some information about Artemis 2. You can see how far away from the Earth they've gone. It does have solar arrays, so that qualifies it. Just like Sebastian's got solar arrays on his vehicle, this vehicle's got solar arrays too. So I like that comparison. That's a good way.
And batteries.
And batteries. Yes, exactly. And batteries. And then, oh, he got a ride in the electric vehicle that goes up and down as opposed to back and forth. Okay, I like that he got to do that. That's good. We had Chris one time as a speaker, and he talked about things that he's always researching and writing about. He appears in the Houston Chronicle and the San Antonio newspaper, I believe. And so, yeah, that's great. So, of course, there's our email, info@houstontxeva.org. And besides looking at Facebook, you can look at Instagram and YouTube, which is where we will put tonight's recording, and you can look at past meetings recordings as well. So, all right. That's it for getting started for our April 2026 meeting. Okay. And Steve, are you out there?
John Haddock, colleague, is also online.
You were a little muffled there. Say that again, please.
My colleague John Haddock is also online. Are you able to hear me? No.
Yeah, because we
Is
put
that better?
Yes, you're sounding better
Steve,
now.
you're showing that you're muted. I don't know why we're hearing you.
Well, I'm on twice. I have a clone. My clone also joined, but
Yes.
my clone had a problem with the computer, so I'm on twice.
Yeah, and we've done that various times with Zoom calls. That's not unusual because it helps with the connections for folks. But good, because yeah, we had both your name, Steve, and John, your name in our email blast that we sent out to between 400 and 500 people now, I believe. 600 people now. And yeah, I was talking to one gentleman named Don earlier today because some of us were out looking at the little robots in the Amazon Fulfillment Center. And they are truly electric, and they know how to go charge themselves when their batteries get worn down. And they move towers of all the items that we're all familiar with ordering from Amazon up at the Ella Boulevard Amazon Fulfillment Center. And Don was saying he was looking forward to getting an EV. So, but he gets our emails. And so it's good to get the word out to other folks that would like to discuss the state of things, and everyone from students up through retirees and soon to be retirees. And so that's good. So you guys out there at Purdue University got a pilot project to install a dynamic wireless power transfer system in West Lafayette, Indiana, where you're at there at Purdue. So we're real excited to hear about it. Yep, I see the first slide on the screen here. So I will hand it over to you, Steve and John.
Okay, thank you. Just to confirm, people can hear.
Yes, we can hear you just fine.
See. Great. And John is going to be talking the civil engineering side of this, and he'll have some comments also, I'm sure, as I progress. It's a pleasure to be here. We're honored to be invited. John and I are two people on a team at Purdue, but also part of a larger team that includes the Indiana Department of Transportation, Cummins. It also includes colleagues at other universities that we'll talk about a little bit on the next slide. But this is a picture of us at the roadway with a vehicle. It's a Class 8 vehicle, and several of our colleagues are there. Nadia Gritza is in civil engineering, Dean ECSL apprentice, Aaron Brovant and Rob Swanson are all with us in ECE and in spirit tonight. So on the left of the slide, you'll see some logos. You know Purdue probably, and Indiana Department of Transportation, they have a program, Joint Transportation Research Program, JTRP. John's an integral part of that. I've been participating through this program, and of course Cummins. But at the top, you also see Aspire, and that's an NSF-sponsored center. It's led out of Utah State University, an excellent campus. They've been a lead. Purdue's been one of the founding members in teaming with them. You see there's a group of institutions, UC Boulder, UTEP down in Texas, Cornell, Colorado Springs, and the whole goal is transportation electrification. It started in 2020. There was a precursor to that, even going back to 2015, and the goal was to improve transportation systems for all and across vehicle classes. One of those aspects that John and I have been focal point, has been our focus, along with the colleagues I mentioned, is dynamic wireless power transfer. And for those that aren't familiar with the term, in dynamic wireless power transfer, there is a coil, and you can think of this for charging of phones. You have an inductive coil. It's the transmitter coil, and there's a device that needs to be charged, and that has a receiver coil. And magnetic fields or time-changing magnetic fields are established in the transmitter, and they are observed and received by the receiver, and that is utilized to charge a battery. And people have applied this to EVs in a stationary setting. That's bottom left. There's actually an SAE standard for this focused on light-duty vehicles. And the convenience that's offered by that of stationary charging is you don't have to mess with a plug. And you can envision that that is a challenge, particularly as you go up in vehicle class and the power levels. But furthermore, there's a second advantage, and if you can do this dynamically, what you have the potential to do, and what we've been considering, is greatly reduce the battery size and leverage the roadway. Not think of it not as a focal point of charging a battery, but actually providing the power that the vehicle needs for propulsion, auxiliary, so that the battery can maintain a state of charge on the roadway. And if you can do that, then you only need the battery to get onto that roadway and to get off of it. You can shrink the size of the battery. And that was a goal that we started on. And the focus became heavy-duty vehicles for a reason, and we'll talk about that here in a second. But our goal is to make transportation cheaper, safer, more reliable, and we focused in, like I said, on heavy-duty vehicles. The key advantages, if we can get this to work, it's a much higher efficiency. I'll just say now that end-to-end efficiency in terms of from the utility grid to the vehicle's battery system, that bus is on the order of 85 to 90%. So very strong. That energy can be supplied to the grid for a number of means. And the challenge is, of course, for electrification, batteries are expensive and heavy, and that's our target, to lower those. And we envision that the DWPT, at least for heavy-duty freight vehicles, could reduce battery needs by a significant amount, up to 90%. So on the right here are figures. They show a roadway. That's a top figure where within there you have to place transmitter coils within the roadway. That is actually something we did under this project. And we have to get the power to those transmitter coils. And you see there, the power is going to be provided by some power electronics units. And just to give you a sense, we're operating those coils at 85 kilohertz. So you can think of your wall outlets in your homes at 60 hertz. To get the energy that we're needing, the power we're needing across large distances of air, we need to go to high frequencies. At the bottom of the slide there on the right is you have a vehicle, and it has to be fitted with an assembly, and that assembly includes coils that are going to receive that time-changing magnetic fields, and then some conversion circuits that enables you to couple into your battery system. Now, if you're thinking about this on the right, as a vehicle or as a Department of Transportation entity, or you're thinking about this as a vehicle owner, you're wondering, is this financially feasible? Because you're putting this into, it's a lot of equipment. And that was one of the targets that we were focused on early in our research around 2019 and 20. And Denise Apprentice, our colleague, led that. This is a detailed slide, but we'll just get to the bottom lines. Dionysius and his student Diala Haddad had come up with a term, the levelized cost of the roadway. Okay, and what does that mean? It means that everybody in your room right now is an investor in a roadway. Your goal is to put equipment into the roadway and be rewarded by, over long term, to have some financial gain. The levelized cost of the roadway is, what do you have to charge to a vehicle operator who's using your roadway and taking that power? What do you charge them to break even over a time frame of like 20 or so years? And it turns out that if you look at the roadways in Indiana, that's the picture on the right-hand side. Levelized cost of the roadway is going to be about, you can get it to about 32 cents per kilowatt hour, provided that you focus on roadways that have heavy-duty truck traffic. This is not going to make financial sense on any roadway. You can see many roadways on that Indiana map. You don't see that many that are in green where it says that you're profitable. Now, there's another side of that equation, and that is the vehicle operators. A fleet owner like an Amazon or a Walmart, they have to make a decision. Should we purchase an advanced diesel engine vehicle, or should we purchase a electric vehicle? And it turns out that if you can get if they can be charged around 30 cents per kilowatt hour for their electricity, it's a win for them. They break even. They're better than that with a diesel engine. And so what you can glean from this is it's a win-win situation, because in Indiana and most way across the country, the levelized cost of the roadway can be in the low 20 cents. So you can make money, and the vehicle operators are happy as well, or fleet operators. So the financial feasibility, the key things about this is you get the levelized cost of the roadway down by servicing. You have to service everybody, but you have to design your roadway system to take heavy-duty truck traffic, and you have to have those heavy-duty trucks on that roadway. And that's what this slide highlights. So that was the feasibility. Now, the technical challenge associated with this is it requires for each vehicle on the order of, or each heavy-duty vehicle on the order of 200 kilowatts for them if it's an 80,000-pound vehicle that's driving 65 miles an hour. And that's a significant challenge associated with this overall system from a technical point of view. And that's made even more challenging because you have to place your transmitter coils below the roadway surface, more than 2 inches below. And vehicle manufacturers like to have clearances, particularly for your heavy-duty vehicles, above 8 inches. So you're talking about over 10 inches of distance between coils, and that's a challenge. So we have high power, long distance between coils. And what we were able to do, and Aaron Brovant, our colleague, led this, is to design a topology that's a 3-phase topology that enables us to do this and do it relatively for relatively low cost. And why is that? Well, it's because we don't have magnetic material in the roadway. The only thing that we place in the roadway are coils. The vehicle receiver also has coils, and it has some magnetic material to tune the flux paths. Okay, so this was something that we had developed at Purdue. It's called a planar transmitter. And the view that you're seeing, just envision a vehicle's in front of you, and it has this system, and you cut it in half, and you're looking at that cross section, and you see these respective coils. I'll show on the next page, this is the actual system that we had tested in our laboratory, and there is the ground assembly that gets placed in the roadway. There's 3 coils there, an A, B, and a C. Each has 2 turns, and then the vehicle assembly as well. And that you can't see the receiver coils other than some end turns, but then subsequent to that, you see some electronics. And we can, after I present and John talks some, we can talk technically in more detail. There's waveforms on the right. You know, we're academics. There's nothing that's going to make us more happy than discuss plots. But for right now, I'll just move on and say, John then led the questions regarding structural and thermal assessment of our system before the instantiation in the roadway. And John, did you want to say anything about that?
No, I'll just point out that we have here at the university, in conjunction with our state DOT, have an accelerated pavement facility, which is what you see there. And it basically, we're able to build pavements in there. And you can see on that top picture, there's a pavement. You can see the coil put in it. And then we're going to put some asphalt in around and over that. And then that machine then is half a semi-axle. So it's basically 9,000 pounds on a dual tire. So that's half of what an axle on a semi tractor trailer would be. And we're able to traffic that back and forth and then get some idea in a controlled environment what the pavement's going to do under loading. And in this case, we had no idea what would happen with these coils under loading, nor did we know what would happen thermally. And so we were doing some thermal testing in a controlled environment as well. So I'll stop with that, Steve. If you have another slot.
Yeah, and John and I will tag team on these because subsequent to those tests, which took a couple years to instantiate and prove out, the Indiana Department of Transportation was interested in going forward and saying, well, how do we actually install this into a roadway system? And that's indeed what we did. The pilot was on US 231, just west of the Purdue campus. And there were a number of goals associated with it, including validating our performance predictions, demonstrating safety of the technology, in advancing businesses that support such efforts on electrification. It was adjacent to a maintenance facility of INDOT's. You can see that on the top left. That provided kind of a support structure for us in constructing the system. The roadway then was, you can see the picture here, there was a multi-step process. This was not a new roadway. It was an existing roadway and it's a concrete pavement, and this was intended to then be retrofitted into that. That is not how it will be done in the future. When this comes to fruition, it'll be placed in fresh roadway, but this is what we were off, or the opportunity that we were given, and went with that. And you can see the different stages. We'll have some slides now that show you each of these stages. And I think this first one, John likes to talk about because he's a pavements expert and can tell you what was done here.
So they're just milling. So you can see the milling machine in the leftmost picture. So they had to mill. Each slab had to have be milled out to about 4 inches deep in order to accommodate the coils. Then you can see in that right upper picture there, we had to core a hole down through it because we had to actually bore into from the side in order to pull all the cables from the coil out to the side of the road so they can be connected to the electronics that were on the force slope. And you can see in that bottom picture there what that hole looked like. It's about a 42-inch diameter hole. And then they were able to bore in from the side and then take the coils, the wires from the coil down and through.
And we had 85 coils covering 400 yards, 440 yards. So 85 coils that are 12 feet long. And the reason for that 12 foot is there were existing metal dowels that were placed between the roadway sections that are in 15 foot long. So we had to stay clear of those. And this was the process where we're transitioning more to the electrical side, where we're now adjacent to the shoulder, and they're putting in channels for conductors, electrical conductors between vaults that house the electronics. In the center picture here, you can see them. John had mentioned the bored hole in each of our transmitter milled sections. They're now running conductor or conduit from there to the side of the roadway for the to be connected to the electrical system. And this just shows that they're preparing. This is that system on the side of the roadway adjacent to the shoulder. There were vaults, concrete vaults that were used to put 2 inverters. So we had one inverter that's purpose is to convert DC power to that 85 kilohertz that's provided to transmitter coils. And we had one inverter per coil. And so a vault housed 2 inverters. On the right-hand side, you can see our coils being fabricated. They were fabricated off-site. rolled up, kind of like a fence row rolled up, and then brought on site and unrolled. And then those long end turns that you see were put into that hole, the bored hole, the conduit there, and brought to the vaults. And John, did you want to just say anything here about this?
Well, that's what they look like. Everything's in place. We're just waiting for the folks to come and put the concrete back in. So we had to patch this with a synthetic concrete, which was done. NDOT chose that material because they had a lot of experience with it on their bridge decks, and it holds up well. But that gives you a really good idea of what those look like as you look down the roadway.
And we had to, the faculty with our students, these are two PhD students, Nick Fronix and Isaac Abram, and we had to test each coil to make sure that it met our target performance. There was acceptance testing, and the bottom right figure is a figure to show there's a x-axis, and it's called the sequence coupling factor, TSCF. Because this is the Masters Week, we'll think about this in terms of golf. Your low numbers are your target. So you want to be to the left. And we had a target of less than 5%. And the bottom line is, even though this was the first ever instantiation here, all of them met that target. And all of them were, or the majority were far superior on meeting that target. We've tested these coils now 4 times through different stages of construction and after weather and traffic, and they've met this and performed exactly the same. So there's been no degradation that we found. And this was what, John, you had mentioned before, the center figure here. If you want
this is the concrete contractor. You can see in the two pictures, well, the left picture and the one in the middle, they're putting the concrete, synthetic concrete's going in to cover everything up. So you get a good look at that. And that's kind of what the road looks like today.
Mm-hmm. And on the right is them putting the inverters into the vault. The inverters were manufactured by a company in Indiana, PC Cross and Associates. They produced those 85 inverters. They're air cooled. So you can see the fins that are facing us on that right-hand picture where the contractor is putting it into that vault. And we did a number of tests. We became more and more sophisticated. We started with this wooden frame where it was our mobile test apparatus. Every day we would, you can't see the receiver coil, but it is present there. It's under the electronics, and we'd bring this out on a trailer, roll it back onto each coil, and do testing of the inverters and the coils. As we were doing that in the evenings, we built the more mobile version of our mobile tester apparatus, and that's on the right. And John's truck is in front of the trailer. The trailer has our receiver underneath, and Vatan Meher, who's our PhD student, is there taking data, not as the vehicle's moving, so don't report that. This was a stationary test. When it was moving, he was in the truck with us. And after that successful testing, we tested with the Cummins vehicle. Our responsibility in this effort was to design the receiver and implement it underneath their vehicle. And then we also had a DC to DC converter to interface, take the energy from the receiver and communicate to the battery/propulsion drive. The way this worked is their control module, the Cummins control module, would send a power command to us. And the DC to DC converter that you see as a gray box there, its whole function in life was to deliver that power that was commanded. Rob Swanson, our research engineer, was instrumental in building the bottom right here receiver unit. A remarkable achievement for an electrical engineer to get this in structurally sound for 65-mile-an-hour tests. So, and Vatan and Isaac and Nick were the ones that constructed that DC to DC converter. They designed it. And this just shows you some plots associated with it. We can go back to these and talk about voltages and current if that's your love, but I'll just point to you to the first thing to say. The green lines are the most important on the plot. Those are the power that the roadway's delivering to the vehicle. So this is the power at the DC bus of the vehicle in green. And then the level that's shown is what the vehicle commanded. So the bottom left shows 50 kilowatts commanded. You can see that the roadway delivered that. There is an oscillation. We'll talk about that here in a little bit, but on average, it delivered exactly what it was supposed to as the vehicle is moving 65 miles an hour. Then the command came for 150 kilowatts, and you can see that that was achieved as well. The achievement comes when you're over the pad. So if you remember, our pads, our transmitter pads are 12 foot long, but that leaves 3 foot of a gap between them. And so you can see this oscillation that occurs. So there's 150 kilowatts, and then it drops. And then it goes back up. And that drop is because we have that the 3 foot gap between our transmitters. Do you have to have that? No, you don't in future roadways. We did because of the dowel rods that were in the existing roadway. This was power transfer at our target was up to 200 kilowatts. We had a battery system that was supplying our roadway, and it couldn't deliver the full power, but we did get to of 200 kilowatts, but we did get to 190 kilowatts at 65 miles an hour. And this was the plot that shows that. The note here is our peak is 190 kilowatts. Our average was about 168. And just looking forward, our Aspire Center has been looking forward to say, when could we see these? And our target was to develop pilots by 2026. This was created many years ago, like in 2021, and we've achieved that. And Aspire is also supporting the development of roadways like this in Florida, some in Michigan. There is one at the inland port, not a full roadway like this, but something where it's quasi-dynamic in Utah at Salt Lake City. And we're anticipating, maybe not in the US, it may be globally where we see this, but in the next 5 to 8 years, we'll probably see longer roadway sections, 5 to 10 miles. And the hope is that this develops, that by 2040, we can see this rolled out on interstates. And Aspire has a target where we would like to see 1,000 miles of roadway with multi-state pilots here by that time. John, did you have anything else you wanted to say?
No, I don't. I think you covered it well. Thank you.
Yeah, thank you. We have one video. This is the truck. And there's more available online if anybody has any questions or would like to see it. But with that, I know we've taken quite a bit of your evening, and so we're happy to answer any questions that you had.
Well, thanks, guys. That was really impressive, and I really like seeing the truck moving down the roadway at the end. You went through all the work that it took to get to that point. I'm glad that we got to see the truck moving across over all those coils and everything that you buried into the vaults and so forth. That's really good. I really appreciate you presenting to us.
You're welcome. We enjoy it.
And we'd like to open it up to questions, both folks online. Colin, if you can look and see if folks want to maybe drop questions into the chat. and for folks in the room. So let me go ahead and pull a microphone over to you.
So what is the Tesla plan, and how does this align with the Tesla plan?
Yeah, so we saw one Tesla vehicle in one of your photos there. Are you guys in contact with Tesla?
We've been in contact through Aspire with numerous groups, GM, Ford, Tesla. We're in the SAE testing with Toyota and Honda. So there is definite interest, but I think their interest is mostly kept quiet. We don't know their full goals, other than I think that they have significant interest in seeing pilots that are even longer and with multiple vehicles and interoperability, which is our next one of the next phases of a future project.
Okay. So thinking of interoperability, I know one of your goals is to reduce the size of the battery needed on a truck. Now, of course, since Tesla was brought up, and Tesla, of course, is planning a vehicle with quite a sizable battery, would you be able to combine your under-vehicle receiver with a vehicle with a full-size battery and therefore give it capabilities of taking advantage of roads that do have the system and also drive on roads that don't?
I think the target would be to take their battery and reduce the size and save costs there and make things even better in terms of environment, and just put the receiver on, interface with their electronics, and everybody should be happy. The one thing we didn't mention in this is with the coil design, the kind of the beauty of our system is it scales with receiver length. So the Cummins vehicle that needs the 200 kilowatt level, it was about 6 foot long, and about 3 feet wide, just over that. But on the Cummins vehicle, if they'd only need 100 kilowatts, then that would shrink. You would only need 3 feet long. So it scales directly. So it's directly applicable to these across vehicle classes.
All righty. So I see the question down below. Whoop, it just disappeared from the screen from John Metric. Okay, here on the side. I don't know if you guys online can see it, LC series or parallel. How do you treat circulating currents when no receiver truck coils nearby? Do you turn it off or dynamically some proximity sensor? And then a second paragraph after that.
In our system, first in our transmitter coils have a compensation circuit. It's called an LCC, so capacitor and inductor, and they do the dancing associated with the coil to do the energy transfer and make sure it's efficient. In terms of engagement of the coil turns on only when the vehicle is detected, and it's I should back up a second. Our first coil is put into what's called a capture mode, and it turns on, and it's as soon as it senses power level increases, it then provides the power to the vehicle, and then also communicates through fiber optic to the next coil inverters to turn on subsequently. And it was all timing based. We didn't have an overly sophisticated means of vehicle detection. It's something that will come in later stages. And so the only thing that occurred, though, is a transmitter would be on only when a vehicle was over top of it.
Cool.
Yeah.
All right. And if you can see the second question down, have you tested actual drag related to the coil coupling? As you drag the coil across, is there any resistance to movement like current does in copper?
You mean, I think the question is about forces being established, Lorentz forces. You have a current in your receiver, and you now have force established because you have those currents exposed to time-changing fields or two fields. And we did calculations early on that indicated those would be very small. And indeed, that was never considered after that. And I don't remember the force values that were established, but I remember them being such that we didn't account for those at all in the development of our receiver and the integration of those onto the vehicle.
Okay, very good. And I see Chris Chen asking how to make older EVs that lack necessary hardware compatible with wireless charging.
John, do you want to answer that? I've answered the first couple. Do you have any thoughts on that?
No, I'm not answering electrical questions.
Oh my. Yeah. The only way to do it is you would have to retrofit. The older EVs, you would have to have a receiver placed underneath the chassis, and you would then have an electronics box that would tie into the DC bus of that system. The Cummins vehicle was it was an older EV, and we did the retrofit, and that's exactly what we had to do. We didn't break into their system at all. They didn't have a lot of software upgrades to make. In fact, they just had to adjust some things to do some CAN communication to talk to us, but nothing overly sophisticated. And so that's kind of how it would be.
All right. And I see again from John Metric, and of course he's really into a lot of EV racing and high performance. He's asking about efficiency versus height relationship.
Yeah. I don't have a direct number for you. I can tell you that a distance from the coils, like I had said, 10 to 11 inches, we were at end-to-end efficiency of about 85%. If you would say, well, you're now going to be at 14 inches or so, you have two things that are facing you. You probably, because of the current handling capability, the size of conductors you chose, you probably couldn't get, you would need extra currents, and you probably couldn't get there to get the power levels at that increased number. And if you could, you would have excess losses in your inverters, in your coils. So but I don't know the number. It's certainly going to decrease with an increase in air gap.
Okay, and what comes to mind for me is whether, yeah, I agree, 190 kilowatts is awesome amount. Smaller vehicles, I mean, you had in some of your charts light EVs, whether say like a personal car could have a smaller air gap and whether you'd gain some efficiency and maybe not even need to go up to such a big number like 190 kilowatts of transfer. Have you looked into
Yes,
that?
you would. Oh, yeah. I mean, you can, it would be up to the vehicle manufacturer in terms of what power level they would want.
Okay.
But they could certainly, if they only needed 100 kilowatts, and this was only a 4-inch off the roadway surface to the receiver distance, you would improve the efficiency. And you would certainly do that, and you could get that higher power or that power level of 100 kilowatts. You could get the 200 kilowatts at that power level, and you'd be more efficient because
Great,
of the reduced air gap.
we do know there are EVs out on the market that through air systems can raise and lower their driving heights. And so there can be situations, I would think, that if you know that you're driving across coils, you would lower your vehicle down and help improve the efficiency. So Christian is also writing, what will be the minimum cost to make those modifications on older EVs for wireless charging? What kind of charging speeds can we expect?
Yeah. I don't know if this group has been around academics, but one of the most dangerous things to ask them is cost. Because, we have a hard time with that. I can tell you, in terms of coils, the receiver system, if we're talking about a one-off, this is going to be expensive because unless you do the machining yourself of the aluminum assembly and putting that all together, I think for us it costs $5,000 to have that aluminum frame assembled. That was the dominant cost. The coils themselves, much cheaper than that, and then the electronics that were above that, cheaper. So that first box, I would say you're talking $5,000 probably if you're doing this one off. Then that DC to DC converter box, that's probably also going to be on that order. So I would say you're talking on the order of 10K to do this as a retrofit. But that cost gets reduced, of course, if you can do a lot of the machining of those parts.
Okay, very good. And have you looked, I think I've read about something along these same lines being developed in Sweden, I believe it was. Have you looked at what's been happening around the world?
Yeah, there are companies in Sweden, NREX and Electrion is another company, and they're doing pilots in Sweden and Japan as well. So it is gaining traction across the globe.
And we have a question in the room. Is there any interference with something that people carry around a lot, like their cell phones?
Yeah,
or a pacemaker.
Right. Right. Well, Aaron Brovant led our coil design, and one of the design specs was the stray field that was adjacent to the roadway, so that the closest somebody could be would probably be at the shoulder of the road, and the standard is 15 microtesla, that level. As part of SAE standards testing in Utah, we were at about 12.5 microtesla, so below that standard. So from that perspective, we think we're good. We're still working on, there is no standard associated with the emission as a function of distance. Could we do interference with other vehicles? We didn't see that. We didn't witness that, and we didn't see it in our vehicle either. Our vehicles worked well, but could it? And certainly you could design the system and operate it incorrectly and cause problems, I suspect, but you wouldn't, because the standards would enforce you to ensure, when those standards come, they would ensure that that's not the case. And that's what everybody in the community is working toward.
Okay, very good. And in reference to companies, I see inverter company in Indiana, PC Cross and PC Kraus Associates is maybe the full name of that company. Okay, good.
Dave, I have a question online.
Yes.
So, Steve, I think the Tesla semis are rated up to like 800 kilowatts. Because my first question was, did you say you guys, this was a Class 8 truck?
Yes.
Okay.
Yes.
So that's semis, and they have load capacities of 80,000 pounds, and then you've got grade levels, right?
Yeah.
So what power limits do you guys think you can get out of the wireless, dynamic wireless systems? Is there a theoretical max or?
No, I think, well, that involves cost and those considerations. I think a reasonable level is on average 200 kilowatts. The power demands that you need, that 80,000 pounds at 65 miles an hour is going to dominate your criteria. If you're wanting to go up significant grades at 65 miles an hour and fully loaded, then certainly your power levels would be much higher than that. But what we suspect you would likely do is your battery will carry you through that. And so you don't need to necessarily just increase the power there. Over these intervals of time, the battery can kick in and provide some of the power while also the roadways providing some of that power over those large grades. So I think in practice, I would be surprised if we see roadways that are designed much above 200 kilowatts.
Okay, thank you.
Over engineering, yeah, because my thought was also, yeah, these trucks go up grades in the mountains and come down and so forth. You don't want to over engineer when you do have some battery capability in the Class 8 truck. Good. Okay. Robert?
Yes, I had a question. I asked it in my email. Scalability, okay, it's one thing to do it on a few miles or less on the back roads, but how can you do this like on interstate highways, and who would pay for it, and how would it be powered? Would we have to have more power stations or renewables at the roadside, or what?
John, you talk about the thoughts on the roadway construction, and I'll fill in at the end on the electric needed.
So obviously the thought is that it'll only be put on roads that have a lot of heavy traffic on them. So for example, in the Midwest for us, I-70 between Indianapolis and Columbus, Ohio, which is wall-to-wall semis all the time. Something like, the 715 that comes out of the port of Long Beach in California, things like that, where there are a lot of trucks. It would go there, but not on lesser roads that didn't have a significant amount of truck traffic.
Good. And there is kind of a connection between Houston and Indiana, actually kind of a broken connection, but you talked about building into new roadways. And I noticed I-69 mentioned across certain sections of Indiana there. You may or may not be familiar that down here in Houston, we have a State Highway 59 that's been renamed I-69 because it's part of the corridor that's supposed to eventually connect between the Mexican border and Canada. And of course, there in Indiana, you've got sections of I-69. So maybe filling in those sections of road and building new roadways, including the coils, would be an efficient way to do it to cover large stretches.
Right. Like Steve said, what we did on this particular pilot project was the exact hardest thing you could do. We retrofitted into an existing concrete pavement.
Yeah.
And you never want to do that again. You want to put it in new pavements as you build them. So currently I-69 for us runs from Detroit to the Kentucky-Indiana border. Indiana and Kentucky are currently building the bridge across the Ohio River for that I-69 extension. And Kentucky is building their portion of I-69 in Kentucky. So hopefully they'll eventually join that up. And, if there's a lot of truck traffic on that, then it becomes a really good candidate for this type of a system.
Mm-hmm. Very good, very good. And I see in the chat question, can you put energy back in the grid going downhill?
We'll talk about the grid because there were two questions about the grid. Do you need new power stations and things? Well, the way we're figuring, if you have this on a single lane of road and you have heavy duty truck traffic and it's servicing everybody that has the retrofit or the new vehicle that has this on it, you're going to need about 2 to 3 megawatts per mile. So the way in early stages of this, talking to different utility operators, we were envisioning and they were envisioning substations probably on the adjacent to the roadway about every 10 miles and servicing 5 miles to their left, 5 miles to the right, and having to deliver on the order of a couple megawatts per mile. For them, that wasn't something that they considered a showstopper. And again, that the question becomes, what is the availability they have at that particular site? But there's also the thought of the roadway operator that installs the system may just say, okay, we're going to put here at that substation our renewables in tandem with a battery bank that would support this, and your grid tie would be for backup. And so this needs to be further developed, but that kind of gives you a target of the level of power. It's nothing compared to the data centers that appear to be taking over our universe. So I think that this can be engineered. Can we put power back into the grid? With our system, no, because our front end, right after our receiver coils, we have a diode rectifier. So there would be no way to send power back through the grid. If we replace that diode rectifier with an active rectifier, we could do that. Yeah, you could send energy back.
Good, because there's a lot of discussion here among our club members. People are often wishing that they can do, vehicle to home, vehicle to load, various things.
Yeah.
So hopefully manufacturers will include that capability in more future vehicles. Good. Okay. Yeah, another question here.
You might have said this previously, but what are the implications of, say, asphalt versus concrete on top? Is there an implication on how much power is actually delivered?
John, you're the pavements person.
Well, we can talk about the materials and how they'll hold up with it, but I mean, part of the question, Steve, I think is does the field act differently in those two materials? To my knowledge, it does not. So it doesn't matter what material you have, you get the same electromagnetic field. From the standpoint of materials, there was an early concern about putting it in asphalt, which, by the way, is much easier than putting it in concrete when you retrofit. The thing that was concerned about asphalt was that the coils were going to produce a lot of heat, and if the asphalt gets heated up, then it can actually rut. And you probably see that from time to time in the Houston area when it gets hot and humid out, that roads can rut that are asphalt. We have not seen that in all the thermal testing that we have done. And in the APT, we actually had the system turned on all the time we were trafficking in, as opposed to the way the system would really work, where it'd be switching on and off depending on when it was being used. So we don't see that as a problem. Concrete could also be a problem if it heats the slab up, because concrete slabs want to warp and curl when they have temperature changes, and that can cause problems. Again, we've done the testing. We haven't seen that, but we continue to do testing, and in fact, are currently trying to model that to see if we can make sure that we absolutely are not going to get problems with either concrete or asphalt.
Okay, good. Thank you. Yeah, it was going through my mind as well. Asphalt, concrete. All right, Robert.
You may have answered this already. So these roads don't actually charge the battery. It's just powers the vehicle. So there's no loss or gain within the vehicle battery, correct?
Well, you can, once you're operating this and you're the vehicle owner, you could use this to do charging of your battery. You certainly can, but what you couldn't do with a 200 kilowatt level is you can't you don't have enough power to both charge your heavy duty truck and provide the power to the propulsion drive. But if, for example, you're at 80,000 pounds and you slowed to 58 miles an hour or 55 miles an hour, then you could do both. You could charge your battery with some of your power delivered and you could propel the vehicle. If you're a Tesla car and you design this to accept the 200 kilowatts, the full power of the roadway, you could charge your battery at 100 kilowatts or 130 kilowatts and use the rest for your propulsion / auxiliaries. So you could do fast charging / powering the vehicle. So you have flexibility there.
Very good. I thought you were going to say something about the speed that the Tesla would get up to, but you didn't give us a number there. Okay.
You guys would know that.
But the thought had occurred to me, obviously, when there's traffic and everybody slows down, the Class 8 trucks are going to be slowing down too. And it could be 55, it could be 50, it could be 45, it could be whatever, depending. So yeah, they're with traffic and accidents on roads and stuff, you can be going at any different speed. Yeah. So
yeah. And in that case, if you're going that slower speed, then you can use the power to charge because you don't need it for propulsion.
Yeah. And I'm always thinking these trucks, they get off of the interstate and they have to go make a delivery or something. That's when they're going to be wanting to use their battery, which, as you've already said, the goal is to have a smaller battery so that the whole vehicle is cheaper to produce and we could have more of them and less diesel exhaust going into the air. Yeah. Good. Okay. Any other questions from folks? Charlie?
Did you mention how the consumer would be charged financially for this?
Did you hear the question?
Yeah. John, did you want to take that or you want me to?
Well, no, I've had that question a lot in various places. So we envision this and the DOTs we talk to, or I should say agencies, because we've talked to toll road operators as well as the power companies. This will have to be a partnership. So what's envisioned is that it'll be like a toll road. When you start taking power from it, it's gonna want to charge you. You're gonna have to have an account, sort of like having a toll road account, so that your little electronic toll road indicator just charges your account, and it would be the same thing. So whether or not the people who are making the power are doing that charging, or if the agency that owns the road is doing that charging, or they maybe employ a third party to come in and do the management and the charging of all those things on the roadway. Toll road operators don't have a problem. They're really good at charging you for things like this. State DOTs, not so much. They have a learning curve to worry about.
Yeah, that sounds very true. The toll road folks would maybe jump on it a little bit faster.
Yeah, they sort of see it as another way to make money.
Sure. Good. Okay. Any other questions in the room or online? Well, this has been very enlightening. We really appreciate you guys taking your time to talk to us here.
Thank you. Thank you for your time. We appreciate it.
Yeah. So you're welcome to hang around. We're going to have Sebastian fill us in on what's happened over the last month. We've seen growth, I might say, in the vehicle between 2 months ago and a month ago. So this will be exciting to hear what's happening here at Rice.
Okay. Hello, everyone. We're the Rice Electric Vehicle team. We're the solar car team that is stationed right down there in the garage right next to the room we're currently meeting in. We're preparing for the American Solar Challenge in 2026 in July. So at this stage, we're currently finalizing our design. Most of it's pretty much finished up design-wise. We're just going out and building it and then correcting some of the things that didn't pass the initial rounds of inspection. Just a couple small things like our latch design for the array and redesigning some of our wheel axles. And so if you are new here, our car is right downstairs and you're welcome to check it out at any time you'd like. Feel free to reach out to us too if there's ever anything you're curious about or you'd like to visit us. And for any of the people online, just feel free to reach out to the contact I'll have at the end. We can tell you all about it if you've missed any of the other updates we've provided. So a brief recap, the American Solar Challenge is actually made up of two events. The first is a track race that serves as qualifying for the second event, which is a cross-country race. So the track race is an endurance race, meaning they give you a set amount of time and they turn all the cars loose on the track, and the team that drives the most mileage wins that event. But it's still a really interesting event. Endurance racing in general is really interesting because there's still passing and overtakes, pit stops, all of the fun stuff that really stress test your design and has been improving a lot with the new technologies we've seen in EVs lately. And then the second event is a cross-country race where they essentially pick two cities in the United States. They actually just announced the route this past week. It'll be down Route 66 a little bit from the track in Minnesota all the way down to Amarillo, Texas. So usually they just pick two cities and have this cannonball style. It is technically an endurance race, but most of the best teams are able to make the entire mileage. So then it turns into who can get there the fastest, who's able to, hold traffic speeds for the longest, not have to pull off and charge, who's able to make all of the hilly terrains and things like that. So it's a really good test of not just EV technology, but also what college students can do, and as we prepare to become professional engineers later. So we're a brand new team, actually, just like Purdue Solar Racing. Our school formerly had a Shell Eco Marathon team, and we revived the team to compete in the American Solar Challenge this year. So actually, almost identical story to Purdue Solar Racing for the Purdue alums in the room. Our goal actually is just to design for the track race for our first event. It saves us, thousands of dollars in logistics to not have to do a bunch of hotel stops and things like that. But it also gives us the opportunity to shadow some of the other teams that are more experienced in that cross-country race. It also gives us the chance to have a more unique design in our car since we're targeting kind of a different scenario than the other teams are. So our car is pretty traditional layout, has four wheels. You'd be able to just sit in it and drive. Wouldn't feel too prototype car, minus the whole like carbon fiber canopy thing. But it's kind of been designed to be fun to drive and have a real advantage in, turns and vehicle dynamics and the kind of things you would encounter in real life driving your car. Where some of the other teams we'll get to in a sec take an interesting approach the other way. So because of our car's design, our main strengths are the carbon fiber chassis. We have a super efficient hub motor. We have a lightweight battery. And then, of course, the vehicle stability we have from our suspension layout. And we'll get to all of those in a bit more detail and recap those in a second. We are smaller than newer cars with larger solar arrays. So strategy-wise, this actually means we want there to be less solar energy. So we're actually hoping there's a cloudy day. The reason for that being our battery pack will be the same size as everyone else's, but our car will be lighter. And then all of that is mainly just for planning. The biggest thing that solar brings to a competition like this is you have to be adaptable because you never know what the conditions will be. And there's not just a set strategy to hold. You have to adapt to the solar conditions in addition to all of the racing conditions, if there's incidents on the track, things like that as well. So our main goal, sorry, is just to um, successfully complete the race. A lot of first year teams, just making it through the 3-day inspection process is a big part of the competition. So we'll be extremely happy if we make it through that and are able to complete a couple laps. So mechanical, as far as update wise, since we had our spring break this 2 weeks ago, and then since then we've gotten a couple of revisions back on our competition reports. So we sent along a couple 53-page and a couple shorter ones, a couple reports that they go through and analyze, lots of different simulations and things like that. So we have to update a couple smaller things, but as far as the main big design objectives go, we've pretty much passed those. We're working on cooling systems right now, kind of waiting for our battery pack to be finished before we start installing those. We're currently putting the brakes in and tuning those. We're fitting new wheel and axle designs. The main goal is that we have the engineering design showcase here at Rice, or at the Ion rather, but hosted through Rice's Oshman Engineering Design Kitchen. And we need a sort of temporary solution to put the car on wheels to get it there. And then we're also integrating some of the fiberglass and carbon fiber composite structures for the battery pack that we talked about in our last meeting. And then setting up a couple workspace things. So like a stand for our top shell so we can separate that out, roll it outside, start doing some solar testing, and start working on getting the battery pack actually installed in the car itself. So here's a couple photos of what's going on there. Top left, that is one of the simulations we had to run for our report. So that's just an impact simulation. There's a couple things we have to meet there. You can see on the photo immediately to the right there, that's actually the wheel axle. So we're just shaping those differently so that way it fits with the brakes, all of the normal car systems like that. You can see our suspension design on the right. So because our car is 4 wheels, it gives it a nice symmetry. It's close to what you would call a double wishbone suspension in a full-size car. So it's very predictable and adjustable. And as you load the car up in turns or it rotates around, it'll be very stable. And then you can see our battery pack, the physical design for it. It'll be made of fiberglass composite structures for now. We did some research into carbon fiber sandwich panels that we'll be integrating in the future. And then as far as our braking system, there's a diagram for that in the bottom right. All 4 wheels have disc brakes. And what we're doing now is playing with the tuning between them. They have what's called proportional valves. So we can change, when you press the brake pedal, how much of that force goes to the front wheels, to the left wheels. And then we also have a second proportional valve in addition to the one that you would find in a normal car that allows us to tune left and right. And so that helps us in case we need to move our ballast around from the left side to the right side or things like that. And so a little bit of context to understand why our chassis is such a big advantage. Most teams are typically starting with a tubular steel chassis. If you look at old race cars from the 60s or 70s, that's pretty much what you would see. You're able to calculate all of the calculations you need to do by hand there. And then on this picture specifically, this is another first-year team we've been talking to a lot at UT Arlington. They'll be a really fun competitor because they're essentially the opposite strategy to us. They're a much larger car with the 6-meter squared array, but a steel chassis. And then we're a smaller car with the carbon fiber chassis. So, it'll be an interesting neck and neck for different reasons race there. And then what our car's advantage is a monocoque design. So instead of being made up of a bunch of tubes, you're able to have the body of the car itself provide rigidity and structure. So instead of tubes, you can see those walls there actually are structural and they're just thicker in places that you expect more load. So that was kind of the motivation for the chassis and mechanical design of our car. That was actually my high school car, or an early version of it. And so that was kind of my motivation for wanting to move to carbon fiber monocoques. And then there's also the layouts. So one of the most interesting things about this competition is that all of the cars look really different from each other and it encourages a lot of creativity. On the left, that car won the cross country race in 2024. That's Michigan's car. It's so, as you can probably tell just by looking at it, extremely aerodynamic, very good in those cross country long highways going from one route to the other, um, and just completely optimized for efficiency there. So pretty much state of the art too. They get lots of interesting corporate sponsors. And then you can see um, what we call catamaran designs on the right. This is another one of the top teams from Europe that will actually be bringing their car to America for this challenge. Um, and you can see they have this one is actually asymmetrical, but it still has that same main idea of a driver half and then a left wheel on the other side. You can also see the little fin they have for stability on the top there. So lots of interesting designs. Our approach is to take the best of both of those worlds. So we have a catamaran design, but it's symmetrical. So we put the battery pack in the right, driver on the left, and then we have a monocoque design, but using carbon fiber. So the majority of our first kind of year was figuring out how to source all of the material for that. And then we also are experimenting with sandwich panel composite structures. So essentially combining multiple materials into your sandwich panels that allow them to absorb more energy. The energy absorbed would be the area under the curve in this graph. So you can see the blue is what just a normal one material would be, and then the green there is our sort of optimal ratio that we're going for. And that allows us to have much more lightweight designs because in impact scenarios or things like that, they absorb more energy. And so it really speaks to the importance of keeping the weight down in an electric vehicle. And we're essentially producing EVs that can perform as well as the more lightweight internal combustion counterparts you would find in like the efficiency competitions in Shell Eco Marathon or something like that, while being able to be fully solar powered and not tethered to any charging network at all. On the electrical side, we split it into a couple different projects. We make 3 of our own electrical boards. We have one that's a main kind of dashboard control system. So it integrates all the different telemetry signals. It's what the driver interacts with on their dashboard. It's actually housed right in front of the steering wheel. And it connects directly to all of their controls that will be on our main dashboard. Then we have a simple low voltage one. That one controls lights. When you press the hazards, it makes sure that both of those flash on and off, and it doesn't override the turn signals or things like that. And then various fault lights for if the car is shut down, different scenarios there, if there's a battery fault. And then it's redundant from the display. It's an actual physical, there's a couple physical like red and amber signals on the dashboard that will be sort of redundant error messages for the driver there. And then a board that will supplement our batteries, our charge controllers, and our motor controllers. And so we're also integrating commercial products for those. We'll have a company called Prohelion makes battery management systems specifically for solar cars and college competition vehicles. And we'll split, or that BMS will manage 4 cell management modules that we kind of talked about our design process for selecting in the last meeting. We'll be using a motor controller from them as well. It's extremely efficient, so it'll pair well with our motor that we have. And then we have currently our MPPTs, so the solar charge controllers, and we're working on setting those up and getting the array actually testing right now. And then there's a couple electrical circuits that we had to design. So a pre-charge circuit. So how does the low voltage battery turn on the high voltage battery and the procedure for that? There's all the high voltage wiring. So we had to, this was a big part of the reports as well, justifying that we chose the right gauge of wire, that we have enough of it, laying out where it'll go in the car, what sections of the car are high voltage, and things like that, as well as fuses, contactors, all of the safety equipment that has to go with your propulsion system. And then we're also setting up wireless communications. Right now we have a sort of Wi-Fi local network that'll interface with that main driver dashboard. And then from there, we have a couple options that we're still experimenting with to get that data from the car to our strategy tent. So here's a kind of overview of what that looks like. So this is everything that will be tied to the low voltage battery, so not necessarily tied to driving the car. So just like a traditional car, we have a 12-volt battery that powers turn signals, all your interior electronics, things like that. A variety of things are stepped down to 5 volts and controlled through Raspberry Pi. So a bunch of sensors. There will be a redundant GPS that'll be a sort of backup speedometer for us. And then a couple of sensors that will interact with the motor controller, as well as driver radios. And then the 12-volt battery itself will also be what turns on that pre-charge circuit that starts the battery, what powers our motor controller, as well as powering the different driver control, so like our cruise control system and things like that, and then the actual driver displays on the dashboard themselves. And all of that will be managed right now by a Raspberry Pi Zero, but we've also been trying out a couple different options there, mainly just wanting something that can survive super high temperatures that it might encounter in the race. As far as high voltage, there's a lot of redundant contactors there. So a lot of this is controlled by the regulations, but there's a big labeled arrow to the side of the car with a big disconnect switch. So if you ever see us on fire, you just run up to that and press it. There's one identical to that for the driver. And then additionally, there's one that disconnects the solar array. But then the other two main disconnects are right after the positive terminal on the battery. So those completely shut down the entire car. And then our 12-volt battery turns on our battery management for the high voltage battery, which is split into 4 different modules that we're currently selecting the cells for right now. And that's kind of what makes up our battery management unit. So I guess if that was a little complicated with all the wiring going around, the main idea is that power comes from the solar arrays, it charges the battery, and then from the battery, it goes to the motor. And then the 12-volt battery is mainly just the powering all of the systems that oversee that happening. And so our battery is another main advantage we have because we're using cells from 18650 cells from a company called Amprius. They have extremely high energy density. They're 300 watt hours per kilogram, which I think we were saying earlier, most cells are around the 140, 150 mark. So if you were able to extrapolate this kind of energy density to full-size EVs, you'd see a huge improvement there. The problem with silicon anode technology is their cycle life isn't great. So with our sort of college scenario where we're building a new battery pack every 1 to 2 years, it's the perfect opportunity to collect data on that and potentially give some research back to these companies to help them improve their products. So there's a variety of specifications. It's 4,000 milliamp hours and very lightweight. But then we take all of the kind of what we talked about in the last meeting, we took all the specs from there that got us to our layout. So this is what we had designed at the beginning of the semester. The kind of essential summary of this is that the rules limit us to a capacity of 5.25 kilowatt hours. And then the interesting thing about that regulation is that kilowatt hours depend, of course, on your voltage in addition to the number of cells you have. So we played around with a couple different layouts of the pack itself, and we settled on one that uses 360 cells, connecting 36 in series and 10 in parallel. And so when I mentioned those modules from earlier, those split that 36 in series by 4 to have groups of 9 in series and 10 in parallel. And that gets us pretty close to that maximum capacity. It only weighs 17.28 kilograms, has a nominal voltage that's also pretty low of 129.6 volts. So in the grand scheme of EVs, pretty small battery and pretty lightweight, pretty efficient. It could support a very high peak power output as well. Those cells are very good in things like drones in addition to EVs. But 12 kilowatts is all we'll be needing for our car since it's so lightweight. And then the battery itself is integrated into a box that's removable from the car. So we could take it out and charge it while we're testing it. And most importantly, we can seal it in the competition So that way they know we're just getting power purely from the sun. Our motor controller is, this is just a commercial product, but it's specially designed and customized for solar racing. So it's super efficient. It works with a variety of cruise control algorithms that we're trying to test. And we're currently working on interfacing with CAN, so the communication system commonly used in cars, as opposed to like SPI or something like that. That way we can interact with our microcontroller and the PCBs we have. And we're exploring options to potentially make a custom motor controller in the future. This might be 2 years down the line, but it's another one of the more cost-effective projects that some of the more advanced teams take on later. And so this is kind of the main idea for that. There was a senior design team at Georgia Tech that took on that project and open sourced it. So they essentially benchmarked the exact same motor controller we're using, and we're able to design something that achieved the same performance, but much smaller and much cheaper, significantly cheaper. So the advantage from that would be designing things ourselves and being able to use newer technologies like gallium nitride transistors that would help make it more, not necessarily more efficient, but a lot easier to manage thermally and a much smaller component. And then our last big electrical advantage is our hub motor. So instead of having a motor with a whole bunch of drivetrain systems, the entire thing looks like it's just packaged into our left rear wheel. So it has a lightweight aluminum enclosure, has a single drive ratio, but that's still good for a top speed of around 80 miles per hour. Combined with that motor controller, you're still seeing efficiencies near 98%. Might be somewhere closer to 96 or something like that, but still extremely high, especially in comparison with combustion vehicles. And it can sustain 5 kilowatts and go up to 12 kilowatts. So just for an idea of how efficient that is, we can hold about 35 miles per hour off of 1 kilowatt, which is about what our solar array will be making, meaning we can essentially drive 35 miles per hour indefinitely, or at least from noon to about 4 p.m.-ish. And then, so this is a slide from a different, from one of the documentations we got, just kind of putting that into perspective. One of the main advantages of EVs in general is just the sheer amount of efficiency you get in your drivetrain, going from an internal combustion engine 25% or even 40% in the most advanced cars possible in Formula One and things like that. You jump straight to 80% in traditional EVs. And then using a hub motor, and especially one that's designed to be as efficient as solar car motors, you improve that even further. And then so a couple images of what we've been working on this past week. We have flexible PCBs that connect to that low voltage board. So that's what our lights are mounted to. And so we just slot those into spots in the car. And that's what will be our turn signals and headlights. For each of those on the bottom left there, for each of those 4 modules in the main high voltage battery pack, we're sorting through all of our high voltage cells, those 18650s we have, selecting the ones that test for the best characteristics. So there's subtle variations in capacity and performance between them. And we have 2 goals there. One is to have the best possible cells we have around 560 total. So we're selecting the 360 best, and then having the cells with similar characteristics be in parallel to each other. Because from the battery management systems perspective, all of the cells that are in parallel with each other, it kind of sees them as one unit. And so it saves you a lot of safety issues and potential thermal issues to have them be as close to identical as possible. So that way they're all being discharged together at the same rate. And so as that testing procedure goes on, we essentially just have a couple cycle testers. Some of our team members take some cells home, leave that running while they do homework. Can't leave them alone, of course. And then once we get those, we just fill in our 3D printed holders until we have a full 360 and are ready to spot weld everything together. And so you can see in the bottom right, that's what the electrical layout looks like. We essentially need to split that into a top layer and a bottom layer to get it to actually fit in our car. But that's what all of the connections will look like in the full 36 series 10 parallel. And then in the top right, that's how our solar array looks. We have 4 square meters of array there, and it's split into several submodules. And so we're working on being able to actually, once the battery pack is finished, be able to actually charge the battery pack from it and ensure that all of that is tested properly. We'll be working on an IR testing, so a photoluminescence testing. Essentially, if you back power a solar array, it'll actually emit a sort of infrared spectrum of light that we'll be able to pick up in our testing. So hopefully, I guess next time we see you guys, maybe in September or something like that, we'll be able to update with what that process looks like. And then, of course, we have a whole operations side as well. So big thing this week is the engineering design showcase. So we're hoping to show off what we've done so far there, figuring out competition logistics, recruiting and planning for next year, potentially proposing senior design projects, especially like that motor controller one would be a really good one if we had sort of seniors with that electrical experience, and then faculty that were interested in helping out as well as figuring out the different practice and testing procedures. We were delayed quite a bit in finishing the car, so making sure we can test the car thoroughly before we actually ship it off to Minnesota is really important there. And then on the business side, we have all of the logistics being run there, as well as the strategy that we kind of talked about in the beginning, sort of abstracting from the engineering side to our race team side, how we actually position ourselves there. We have a 501c3 nonprofit that's for us that allows us to kind of make contracts with those companies that we want to work with in the future. So maybe like a tire sponsorship or something like that. And other kind of relevant things. So like that battery cells suppliers, things like that, and machining partners for wheels, and other mechanical parts. We also hope to get more involved in the community, take it to once it's finished, take it to like science fairs, things like that, local educational events, and then of course raising all of the money and managing the accounting to operate all of those expenses. So we've raised a significant amount, and we're pretty comfortable now in that we will at least be able to finish the car and have a decent platform for testing and upgrades. And then we're just looking for a little bit more to cover logistics and actually getting to the competition. And then for next year, so we're expanding we're a full club now that's open to all of Rice, so not just engineers. We're designing a new car for 2028, and then using what we've learned from this year testing and designing all of our battery pack and things like that. We have a good idea of what we would look for to improve those, mainly using 21700 cells. There's also that same company that makes the silicon anode cells is also looking into even higher energy density 21700 cells that could potentially bring our energy density up to 350 watt hours per kilogram. As well as our solar array, there's a lot more efficient options we could go with there. And with regulation changes, we can even make it bigger. And a couple mechanical things as well. So we're looking into making carbon fiber wheels. That would be a big deal for Rice because we'd be one of the few places able to actually make molds and carbon fiber parts here in-house versus needing to use an external workspace for that. Figuring out a tire sponsorship, that's another big business side thing there. And then reinforcing some of the suspension parts, especially in the rear where it has a sort of motorcycle style trailing arm suspension. So reinforcing that to, I guess, stand up to Houston roads a little bit better. And then, as we mentioned, some of those electrical parts that we buy from different engineering companies, we hope to, as we become more proficient and understand how these things work, sort of reverse engineer and work with the software suites for them, being able to sort of recreate those. So the motor controller would be the best cost advantage to do ourselves, but there's also teams that make their own solar charge controllers and battery management systems, a lot of the electrical side there. It just depends what your electrical team is kind of looking to do at the time and how much experience everyone has. But there's a lot of opportunities to make it even better. So we're excited to start working on next year too. And yeah, so that's our April updates. Thank you guys all for being here today. We're excited to have Electric Vehicle Association meeting here. And definitely keep in touch with us. A lot of us are going other places for summer break, but we hope to see you guys in September and August when we get back.
That's great. Thanks, Sebastian.
Thanks.
So if you want to just stay up there, do we have questions in the chat here, Colin? Okay.
Yeah.
Robert.
Basically, to what end are you developing all this technology and these systems and these designs? Is it to advance autonomous vehicles, like small autonomous vehicles that deliver, like Amazon? Is it to advance passenger vehicles, or what? I know there's more than just a race behind this.
So it depends on your scope. From our perspective, it's essentially an engineering and student training opportunity. There's a variety of different competitions. There's like Formula SAE, things like that. They have a much larger presence in Europe as well. So typically it's like what we're hoping to get is an internship at a company that sponsors us. So the ideal situation is get a sponsorship from like, Apple sponsors MIT, Ford sponsors Michigan, something like that. And then they know, oh, you worked on this team, you know how engineering works, and they're more willing to hire you. So that's from the university perspective, what we're trying to do. From the competition perspective and from like the people setting up the American Solar Challenge, a lot of it is kind of incentivizing those newer technologies that aren't ready for the scale of full-size EVs yet. So like those silicon anode batteries, they don't exactly have the cycle life for that yet. And with just a 5 kilowatt hour battery pack, it's much more manageable to actually have a bunch of college students go out and build that. It's not a super dangerous voltage either. It's only 100 volts or so. So it keeps everything at a scale that's still manageable for college students, still a good learning experience, but also still finds the right balance of being, it's not some small RC car that's being driven in a gymnasium somewhere. They're full-size cars that are driven on racetracks. So it kind of finds that balance there. And especially in the 90s, which was kind of considered the peak of solar racing, it's arguably getting back to another one of those. But you saw things like lithium ion cells being used for the first time. Solar efficiency increased a lot back then as well. And aerodynamic design, especially on the mechanical side, the tools and computer software people use to do those has changed so much since then. And a lot of the advantage of doing this is that it trains people that actually understand how to use that, and they go on to work at Tesla, Lucid, and these places that then go and make commercial EVs later.
Out of the box type of thinking that's not already molded by a corporate structure. Is that correct?
Yeah, exactly.
And get a good grade. Yeah. So I saw Kevin Douglas asked, can we get a tour of that area? And Kevin, if you're talking about where the car is here at Rice, yes, we do that every month here right after Sebastian.
No, I was asking where where at Rice the battery is being put together.
The battery. Oh.
So it's the cells are being stored in that same workspace right now. They actually are just in 2 cardboard boxes. What we're doing is taking them. A couple of team members have testers, and so they'll take 8 cells at a time and run those through those. And then we're just putting all of the information in an Excel spreadsheet for now. When the battery actually gets assembled, that will be here as well, because there's a nice big garage door opening. So we're able to kind of keep it away from all of the areas that the safety department is wanting to avoid. It's kind of a precarious situation building battery packs here. So the nice thing about having the garage is it's a good safe space to assemble the battery pack as well.
All right.
Yeah.
Yep.
Yeah.
Okay, so first one, you said 4-wheel disc brakes, but do you have a brake assist, like an electronic brake assist, or how do you actually physically brake?
Okay, so the brakes are purely mechanical. Like if you press the brake pedal, we have regenerative braking too. It just isn't tied to that pedal. What it'll be is a knob on the steering wheel. And so the driver will essentially, like if you were using one pedal driving in a Tesla or something like that, you would set the setting you want that to be at, and then it's controlled by letting off of the accelerator. But then it can also be turned off completely just by twisting that knob.
But you also have like a physical
Yes.
press. That's just based upon how much power your leg delivers to the brake pedal, right?
Yes, and
Oh,
that's
okay. So
to
no brake assist system or anything.
yes, and so there's no ABS either.
Right. Okay.
So things like that.
Okay.
Just purely hydraulic. You push the pedal, it squeezes the
Oh, it is hydraulic.
yes.
Oh, okay.
Yeah.
Okay. Got it.
Yeah.
Okay, cool. And then is this like football teams, like the schools with the most money get the best stuff, like the best solar arrays and the best carbon fiber and all of that? Or I mean, is
Yeah.
that kind of what you're competing against?
Yes, so that's a big part of why it's a big deal that we have a carbon fiber car. We got a lot of help from a university that had access to things like that. Especially if you look at like Michigan's budget was around 2.2 million 2 years ago. So we essentially can't compete with things like that. But it's another part of why we chose this competition is that there's a lot more benefit to, unique designs. There's places to carve out your niche. As I mentioned, we're targeting our car for, the track race, on this like interesting year in between design like regulation changes. So there's not many other teams with a car designed like ours. So that narrows down the competition a lot. Um, and then additionally, because there's such radically different designs, like some cars have three wheels, all these crazy things like that, your money goes into enabling those things to happen. So those teams with the $2.2 million budgets are spending it on like advanced fiberglass molds and renting out ovens from facilities that can fit a huge 6-meter car. Whereas if you look at like Formula One or something like that, they're needing to spend millions for just a couple percentage points in improvement, getting like a whole bunch more compute power for aerodynamics and things like that. So ours is a much more binary, like, can you build your idea, yes or no, versus like, can you afford, a more advanced version of something.
Thank you. Oh, Robert. Okay.
Have you thought about really going outside the box, like maybe like having micro wind on your vehicles, or maybe some kind of sail, or is that not allowed?
Funny you should mention that actually. So a lot of slides, I guess. That car on the right, that's actually what that is, or at least how they advertise it. That fin on the back is technically a sail, and it does generate some positive propulsion as it's going through, if you're able to get enough side wind to actually tilt it at an angle. I think the real reason that became a sort of gimmick lately in solar cars is in the cars on the left that look like that, or I guess actually on the catamarans too. Once they got really lightweight and they were a bit smaller, they started getting pretty unstable in the Australian race that has like 40-mile-per-hour crosswinds, things like that. And so what they were really doing is putting a thing to stabilize their car and keep it from flipping over, because it's actively controlled, so you can tilt it, use it sort of like a vertical stabilizer in a plane. But then they would advertise it kind of as what you were saying, a sail that gives you some positive propulsion forward.
Okay. More questions in the room or online? Well, that was super informative.
Yeah.
Thanks so much, Sebastian.
Thanks for having me.
Yep. Okay. Thanks, everybody. So that, unless there's any last minute announcements anybody's thought of, that wraps us up for April. And we will have our Kevin Douglas run meeting in May. So thanks, Kevin, in advance for offering to do that. He's one of our officers. And we will see everybody next time we see you. Thanks.
Thanks, everybody, for running the meeting. See you guys next month.